Okay, hello everybody. Welcome to electronics. This is going to be the first of the sessions, and we're going to break electronics down into several small pieces. This video is going to have to do with um, the atomic theory. So we're going to do some atomic theory review to begin with, and so let's go ahead and get started on that. See, I've got here a little bit of a diagram for you. Here we have the nucleus of the atom, and then what we know is that the electrons actually set up in shells, moving outward from the nucleus, and different numbers of electrons depending on which shell they're in. So what I'm going to do is I'm going to show you a little bit of an idea. This would be the electrons sitting in those rings, those shells, and in the first shell, we'll have as much as 2 electrons that will set up in that shell. Moving to the second shell, you can have as many as 8 electrons that will set up there. Moving a little further out into the third, you can have as many as 18 electrons. Now, what would happen is with larger atoms, as you would go out, the numbers get higher and higher. Next rings will go up as high as 32, but the atom that we're gonna explore, that I'm going to show you here, actually only has 29. So if we do a bit of quick addition here, we're going to see that we've got 2 plus 8 is 10, plus 18 is 28, and that means that in my outermost ring, which we call the valence shell, we only have 1 electron. And so what we have here then is an element. Its atomic number is 29, and it is copper. So as you can see, I've got the symbol here for copper, number 29. And what happens is, seeing as we have that outermost ring with just 1 electron, let me show you the atom. You have the rings all full. It's really what happens with that last electron in the outside that determines whether a material makes a good conductor, or an insulator, or a semiconductor. And so what happens is, seeing as there's just 1 out there with copper, if you get a mass of these atoms all together, it's very, very easy matter for 1 electron to from another atom to come in and hit this one and dislodge it, and then it becomes replaced by the electron from the other atom. And so what they wind up doing is just kind of moving back and forth and being hit back and forth. And so what you get is this movement of what we call free electrons. Free electrons. And that movement, as we were aware of the flow of electrons, we call current, or amps. And so really it's the number of free electrons in a material that determine how effective a material is at being a good conductor. The next characteristic of copper that's very important is the fact that it's actually non-magnetic. And interesting factor is that because we take copper and we wind it into coils like this, and then we pass current through that coil, and we know that what happens is, basically, we're going to make an electromagnet. Okay, so we align all the domains and we have flux going through here and we create electromagnets. If in fact copper was magnetic, the actual magnetism of the copper material would fight with the flux that we're developing from our electromagnet, and it would greatly weaken or possibly make it pretty much almost unworkable as a material for us for coils and contactors and things like that. So very, very important, in fact, that copper is non-magnetic. All right, the next aspect of copper, very, very important. We're all aware of the fact that copper has a high conduction rate in terms of current, and a very, very important feature that we depend on a lot, using it in conductors in our systems. But just as interesting and just as important actually is the fact that it has a very high rate of heat conduction. Now, if copper did not have a high rate of heat conduction, in fact, then the conductors would become extremely hot just from the normal current running through them, and that heat would dissipate very, very slowly. And so what would happen is it would tend to break down the insulation, and it would really, really limit our ability to use copper as the conductor, the great conductor that it is. So the fact that it dissipates heat very rapidly compared to many other materials, uh, almost as important as the fact that it has a lot of free electrons and is great for conducting current. All right, moving ahead to the next important aspect of copper is what we call malleability. So copper has this very interesting characteristic. You can take a large round of copper like this, and what they do is they actually pull it through dies of reducing sizes like this. And as they pull it through, it becomes thinner and thinner and thinner and thinner. So you can take a very large piece of copper, a block of copper like this, and by the time they've pulled it through an extruder, you'll have a coil of very, very, very fine wire. And so what happens is we're able to take this and actually, without breaking it, we can actually take and shape it and form it. The other thing that's very interesting about copper is that, for instance, if you have a conductor like this, you take it at the end and you make a nice bend to wrap around a screw, and this point does not become weakened. And so what you can do is you can tighten this down, put a screw over this, tighten it down, and it doesn't actually weaken at this point. So for instance, with aluminum, just a small score mark on here, and the whole end of that will actually break off. So copper is not like that. The malleability, very, very important feature of copper for us in the electrical trade. All right, we need to take a look at copper in terms of its oxidation rate. Now, most materials, when exposed to atmosphere, will develop some sort of an oxide layer. Copper is no exception. The rate of oxidation is fairly slow. So I would say for copper, it's slow. Um, a material that actually oxidizes very rapidly in comparison is aluminum. And as many of you know, when we use aluminum conductors, we have to coat them with antioxidant, and that's to prevent, particularly to prevent the oxidation under lugs and terminals where we're doing up connections. And so we definitely have to use the antioxidant on the aluminum. Copper, we do in some cases use some antioxidant on them, not usually as important, but it is interesting that in some atmospheres, even a very small amount of oxidation on a copper conductor can affect, for instance, the ability of a relay contact to pass very small currents, particularly at levels of around 5 volts. Even a small amount of oxide will be enough to prevent actually initiating a current. And so if that's the case, we actually usually go to something, there's another material that has an even slower oxidation rate than copper. And if it wasn't for the cost of it, um, we would probably use it a lot more, but it's gold. So if we need to use some contacts, for instance, that are going to oxidize extremely slowly, and we call them low impedance contacts, they'll actually be gold plated contacts. And and so that very, very slow rate can be beneficial in some certain small applications. But for the most part, copper, the oxidation is slow enough that it's not a big concern. So it works out quite well. We know that the oxide on copper, when it forms, is actually kind of a green color. We call it patina. And many of you are familiar with, for instance, the roof on the Hotel Vancouver. That's the look, that green look as the color that once the copper has oxidized for many years. And it's quite attractive. All right. One of the interesting things about copper is that the conductivity of copper uh, definitely changes a little bit with a change in the temperature of the material. And the way that we describe this is we call this, for copper, we call it a negative temperature coefficient. And what that really means is this: as temperature rises, okay, so this will be temperature, what happens to the conductivity? Well, it actually goes down. So conductivity goes down as temperature goes up. So this material actually has what we would call an increase in resistance, or the inverse of that, of course, is to say that it has a decrease in conductivity. So an increase in resistance or a decrease in conductivity. But in terms of talking about its temperature coefficient, we're comparing temperature to conductivity. And so we say negative temperature coefficient. Temperature goes up, conductivity goes down. Temperature goes down, conductivity goes back up. Another way of saying that would be to say that as load current, if you think about it, as load current flows through the conductor, the temperature of the conductor will increase just due to the current heating effect in the conductor. And as that temperature rises, it would actually tend to cause a slight decrease in conductivity, or we could say an increase in resistance. And that, in fact, will tend to self-limit. So in other words, as the conductor gets hotter because of current flow, the current flow will actually decrease because of the negative temperature coefficient. Okay, the next thing that we really need to take a look at, important concept, is it's quite important, used a lot in the formulation of molecules, something called covalent bonding. And I'm going to give you a couple of examples of covalent bonding. One of them that's actually very, very common. A lot of people aren't aware of it. And then secondly, I'm going to move on to a second example that is really in the semiconductor field, which of course is very important for the electronic components that we'll be discovering and talking about. Okay, so the important thing for us to look at with covalent bonding is what we're doing is really the sharing of electrons between 2 or more atoms. Okay, and the first example that I'm going to give you of this is actually going to be it's going to be a molecule that's made up of 3 atoms, and quite an interesting one to take a look at. Okay, what we have here is we have one atom of this element, and this large one right here in the middle, what we have is the inside shell just has 2 electrons, and the outer or the valence shell actually has 1, 2, 3, 4, 5, 6. And so I've indicated those with these electrons are done with the black, solid black, okay? So you can see there's 2 inside and 6 in the valence. Now, a full valence would be 8, but this one only has 6. So the total between the 6 in the valence and the 2 on the inside ring gives us a total of 8. Okay, and that's actually the atomic number of that element. Now, down here, we have 2 more atoms. These are a different element, and these ones here, you can see the nucleus in the middle, and I've drawn their electrons, you can see with a just a crosshatch in the diagram. Now, very interesting what happens here. This valence shell would like to be full. It would like to have 8 electrons in it. And so what happens is, here's how the electrons share part-time. So this single electron, which is what this element has, it only has 1. Okay, so here we have a material that only has 1. And that 1 is right there. And what it does is it shares part-time into the valence of this element, making it a total of 8. 1, 2, 3, 4, 5, 6, 7, 8. And the interesting thing is how many electrons would fill the valence of this element. And we know that the first or the inner shell should have 2 electrons. And so now what happens is part-time, one of the 6 from this larger atom actually comes out and circulates into this ring, filling it up. So now what we have is the sharing of electrons to make sure that this atom always has 8, and this atom always has 2, and this atom always has 2. We say always, it's a bit of a figure of speech because they're just moving back and forth very quickly. And so what we have here is a very, very stable molecule. There are no free electrons. Everything is, everything's full. And so what we have here, of course, is hydrogen, and here we have oxygen. And this molecule we know as H2O, or water. Okay, so water, many people are not aware of the fact that water is actually held together by this concept of a covalent bond. Okay, now moving a little closer to the electronics. The next covalent bond that we're going to look at is the covalent bond that occurs when silicon crystal is basically formed, forms into a structure that we call crystal lattice. Crystal lattice. Now, if we take a look at just the pure silicon, let's take a look starting with the nucleus here. We start our first ring, 2 electrons. Second ring, 8 electrons. That gives us a total of 10. Now, the next ring would also be 8. And in order to be completely full, we would need 8. In order to be a great conductor, we would want just 1 there. But in fact, because the atomic number is 14, what we have in there is just 4 electrons. So it's really, what we would say is just half full. And so what I need to do is I'm gonna draw a little bit of a diagram of the crystal lattice structure. Then I'm going to explain it to you in a little bit of detail so you can see how it goes together. Okay, so here what I have now, just a small cross section. I've shown you the I've shown you the nucleuses of, actually, I'm just going to use a sample here of nine Si atoms. Okay, these are all the same. I've shown them in different colors so that we can keep track of their electrons. So what I'm going to do now is I just need to fill in and complete for you. We're going to put in just the valence electrons. That's all we're concerned about. The inner ones we're not that worried about. We just want to know what's going to how are the valence electrons going to interact with each other. So let me just start here like this. Now there's the 4 valence electrons that are going to go with that. This one here. Here are the 4 for that one. Here are the 4 for this one. Here are the 4 for this one here, down in the corner. And let's go with all the solids. Here are the 4 that are going to go with this atom here. Now, moving to the others, let's take a look. And this is very interesting what happens. Here we have 1, 2, 3, 4 electrons with this one. Here we have 1, 2, 3, 4 electrons with that atom. Let's move over to this side. 1, 2, 3, 4 there. And just one left. 1, 2, 3, and 4. Now, if we were to expand this out into a much larger section, you'd have more samples of what happens. But we can just look at the center one. Let's just look at this atom right here. And what you're going to notice is that between the shared electrons in the silicon, in the crystal lattice all the way around it, essentially each of these atoms has now, between the shared electrons and their own electrons, it has a full valence. And what that does is it makes this material non-conductive, and what we would call a net charge of 0. Okay, there's no either negative or positive charge. Negative charge, of course, would be from an excess of electrons. A positive charge would be from a deficiency of electrons. This material has a net charge of 0. It's absolutely in the middle. And so, in fact, crystal lattice, silicon crystal lattice that we will use for making electronic components is not a conductor, actually, at this point at all. Doesn't conduct. And so we actually have to treat the silicon in a certain way. We have to manufacture it in order to make semiconductor out of it. Okay, the next thing that we're going to take a look at is, we don't need to look at the whole thing, but we do need to take, I'm going to show you a small excerpt of the periodic table. And we need to take a look at silicon, and then we need to look at the elements that surround it, because there's something interesting that we're going to do with the actual pure silicon crystal lattice in order to make it usable for us in terms of electronic components. And so let me just show you a quick sketch of the elements that are going to be important to us for that. Okay. Okay, so here we have a small section of the periodic table. Let me just run through these, and just so we're aware of what they are. Let's start over here with 29. This is copper. 30 being zinc, 31 gallium, 32 germanium, and 33 arsenic. Now, germanium, we used to talk about that as a material for semiconductors. I just like to highlight that that's really not used. It was was fairly unstable in terms of making diodes, and it's simply just not used anymore. It's pretty much obsolete for that. So whenever we talk about diodes, basically semiconductor PN junctions, we're going to be using silicon for that. Okay. Below copper, we're moving up to silver and gold in the larger, but in the same column, in other words, the same number of valence electrons. So really the number of valence electrons as we move across, and we're just going to talk about the valence. Here we have just one valence electron, okay, just one valence electron. And if we move to zinc, here we have two valence electrons. And if we move into like aluminum, boron, gallium, these ones are actually now at 3 valence electrons. Silicon, we've already talked about. We know there's actually 4 valence electrons. And as we move past into the larger atoms, these ones being phosphorus, arsenic, and antimony, and these ones we're now looking at 5 valence electrons. Now, what's interesting about this is that we can actually take some of these materials and we can use them as what we would call impurities. And we use them for a process that we call doping of the crystal lattice structure. Now, impurities makes it sound like something that you swept up off the floor. In fact, they're carefully chosen materials and very, very specifically manufactured and placed really at the one atom at a time into the crystal lattice to form a structure that is useful in whatever type of component you're actually wanting to build with it. Okay, now if we take a close look here, what I'm showing in the center is this would be some of the silicon crystal lattice structure. What we have there is 4 plus 4 electrons shared together in a covalent bond, giving us 8, which means full, no charge, no free electrons. Okay. Now, what would happen is if we were to take, on this side, we took silicon, and we were to take some small bits of impurity, either boron, gallium, or aluminum, and we were to use any one of these and mix it in and basically place those into the crystal lattice structure, something very interesting would happen. These materials here all have just 3 valence electrons. And so what would happen is we would wind up with a material that overall would be missing a few electrons. So we would say it is deficient of electrons. Now, if we were to move over to this side and we took a sample of the crystal lattice and we were to dope it with, for instance, phosphorus, arsenic, or antimony, the interesting thing that would happen is now we would have a material, a crystal lattice structure, and it would have overall, not very much, but it would have a small surplus of electrons. Now, if we have a material and it has extra electrons, what that means is that this material has a net negative charge. And if we were to move over to this material, and what we have here, we're actually short some electrons. So really what we have is holes in the material where electrons would nicely fill in, but we don't have those electrons. And so in fact, what we have here is a material that on the overall, on the whole, has a net positive charge. So positive charge, negative charge, whereas the actual silicon crystal lattice structure in the middle has 0 charge. This material right here we call P-type material. And this over here we call N-type material. So P-type and N-type material. N-type is made by doping with with materials that have five five electrons in their valence, whereas p-type material is made by doping with impurities that only have three. Okay, so shows you where the p and the n-type material really comes from. Okay, what we're looking at here is this is in fact I've just shown a section of silicon crystal lattice, and these small bits are really just impurities as they've been placed into this structure. So you can see there's just some strings, some chains of those atoms that have been placed into that. And the interesting thing is this is done at such a small, just a miniature scale, that in fact they can place these impurities on um, pretty much in single atom applications, and they can basically, depending on how they lay it out, that is literally the track that the current will follow through that piece of silicone material. So remember, without the impurities on here, this is completely full with eight electrons in the valence, not conductive. So the only thing that actually makes this conductive is the fact that it actually is doped and has those impurities, in some order in that piece of material. And that's literally different types of components are done using specifically doping in different patterns. Now, the last thing that I want to talk about when it comes to semiconductor materials is the conductivity of the materials. So semiconductors. Now semiconductors have what we call a positive temperature coefficient. Now we just talked about the coefficient just a little earlier when we looked at copper. We talked about the coefficient. The coefficient of copper, of course, is a negative coefficient. Now with semiconductors, it's positive. Now what we're really saying here then is that as temperature rises, so in other words, as this material gets hotter, its conductivity also rises. Or we could say that its resistance actually goes down. And so if you stop to think about this for a moment, this is the sort of thing that could cause a little bit of difficulty with electronic components. You start running current through a device. The device gets hot. As it heats up, it becomes more conductive. So that means that for a given level of voltage applied to the component, more current is going to flow, which means even more heat, more temperature. And so what happens is really the heat buildup on electronic components rises in this way, okay, on a real curve. And so what happens is, in fact, the semiconductors, as they pass more current, they will fail very rapidly because the heat's going to build up and it's going to destroy the component. So what we would say then is that for semiconductors, the real enemy is heat. So if we can keep these things cool, then they maintain a fairly stable level of conductivity, and that's what we're looking for. But with electronic components, all types of electronic equipment, if you can keep them cool, they normally operate to their full life expectancy. But as soon as the temperature goes up, the smoke tends to come out. And once the smoke's out, it just doesn't go back in. Okay, that gives us a bit of an idea of exactly how the semiconductor material comes to be. And what we need to take a look at next, so in the next recording, what we're going to take a look at is, now that we have this p-type and this n-type material, what exactly are we going to do with it? How are we going to combine them? And how are we going to use them to our advantage in a number of different components?